Imagine wanting to go somewhere far away, really far, across the galaxy maybe. Right now, if you want to travel, you have to move. You get in a car, a plane, a rocket. You physically move your body or your vehicle from one point in space to another. It takes time, a lot of time, especially for long distances. Even at the fastest speeds we can manage, space is just huge. But what if you didn't have to move? What if you could get to that distant place without ever feeling like you left your living room? What if the space around you moved instead? This isn't just a wild dream, it's an idea rooted in some pretty heavy physics. It's about manipulating space-time itself. It's about travel without moving. The speed of light is a big deal in our universe. Nothing with mass can go faster than light. That's a fundamental rule. It means even if we built the fastest ship imaginable, getting to the nearest star would still take years. Getting to another galaxy? Millions of years. That's not practical for a human lifetime. It makes the universe feel incredibly vast and lonely. But what if there was a loophole? What if you could trick the universe? That's where manipulating space-time comes in. It's not about you going faster than light. It's about making the space itself move, or bend, or fold, so that the distance you need to cover shrinks or moves you along. One of the most famous ideas for this kind of travel without moving is the warp drive. You might have heard about it from science fiction. The name suggests something going really fast. But the core idea is actually much more elegant and, in a way, much weirder. It's about not moving at all, at least not in the traditional sense. Picture this, you're in your spaceship. Inside your ship, everything is normal. You're not feeling any G-forces. You're not being pressed back into your seat. You could be drinking coffee, reading a book, just like you would on Earth. But outside your ship, something incredible is happening. Space itself is bending and stretching. This concept comes from a physicist named Miguel Alcubierre. Back in 1994, he published a paper outlining how something like a warp drive could theoretically work within the framework of Albert Einstein's general theory of relativity. Einstein taught us that space and time are not separate, fixed things. They're woven together into a single fabric called spacetime. And this fabric can be stretched, compressed, and curved by mass and energy. That's what gravity is. Alcubierre's idea was to create a warp bubble. Imagine a football-shaped bubble around your spaceship. Inside this bubble, space-time is flat and normal. Your ship isn't moving fast relative to anything inside the bubble. It's just sitting there, effectively still. But the trick is what happens outside the bubble. In front of the bubble, space-time would be compressed. It would effectively shrink the distance to your destination. And behind the bubble, space-time would expand. It would stretch out the distance you've already covered. It's like space is being pushed together in front of you and pulled apart behind you. And your ship, sitting in its little flat bubble, is then carried along by this moving ripple in space-time. Think of it this way. You're on a moving walkway at the airport. You walk along the walkway at a normal pace. You're not moving very fast relative to the walkway itself, but because the walkway is moving, you cover ground much faster than if you were just walking on the stationary floor. In the warp drive analogy, your ship is walking at a normal pace inside its bubble. But the walkway itself, space-time, is what's really moving, and it's moving incredibly fast. And this is the key. Your ship isn't violating the speed of light locally. Inside your bubble, you're not going faster than light. The space around your bubble is what's being manipulated, what's compressing and expanding. It's not you moving through space, it's space moving you. This is how Alcubierre's warp drive gets around the cosmic speed limit. It respects the local speed of light limit, but allows for effective, faster than light travel across vast distances. It sounds perfect, doesn't it? Instantaneous travel, no G-forces, just sitting there while the universe whisks you away. But there's a huge catch. A really big one. To make this warp bubble, to compress space in front and expand it behind, you need something called exotic matter. Exotic matter isn't just some weird-looking rock. It's a theoretical substance with very unusual properties. Specifically, it needs to have negative energy density. Most matter we know, like you, me, our planet, has positive energy density. It has mass, it attracts things with gravity. Negative energy density is the opposite. It would effectively push space apart or repel gravity. We don't know if exotic matter exists. We've seen hints of something similar in quantum physics, like in the Casimir effect. That's where two very close metal plates in a vacuum experience a tiny attractive force because of quantum fluctuations, and some interpretations of this effect suggest small regions of negative energy density. But these are minuscule, temporary, and nothing like what would be needed for a warp drive. To create an Alcubierre bubble, you'd need a lot of this exotic matter, an amount that's probably beyond anything we can currently imagine. Some calculations suggest you'd need the equivalent of Jupiter's mass, or even more, converted entirely into this hypothetical negative energy substance. That's an astronomical amount of something we don't even know how to find, let alone create. And even if you had this exotic matter, the energy requirements would be immense. Powering such a device would demand energies far, far beyond anything our civilization currently produces. It would make our largest power plants look like tiny batteries. We're talking about energy levels closer to what stars put out. There are other problems too. Imagine you're flying along in your warp bubble. What happens when you stop? All the particles, dust, and radiation that were swept up and accumulated in front of your bubble would suddenly be released. It would be like a cosmic shotgun blast, a burst of extremely energetic particles directed at your destination. This can be devastating for whatever is at the receiving end, including the planet you're trying to visit. It can also destroy your own ship as it stops. Then there's the question of control. How do you steer a warp bubble? How do you see where you're going when space itself is bending around you? You're inside a bubble of normal space, but the light from outside is being distorted. It would be like trying to look out a window where the glass is constantly changing shape in extreme ways. It's not clear how you would even observe your destination, let alone navigate towards it precisely. And some physicists worry about causality violation. This is a fancy way of saying time travel. If you can move faster than light effectively, it sometimes opens up theoretical possibilities for sending information, or even yourself, back in time. This creates paradoxes that our understanding of physics struggles with. Could you go back and prevent your own birth? If you did, how could you then go back in time? These paradoxes suggest that if warp drives are possible, they might have restrictions that prevent such time travel. So, while the Alcubierre drive offers a tantalizing vision of travel without moving, it hinges on theoretical concepts that are currently far beyond our grasp, or may even be impossible. It's a beautiful piece of theoretical physics, but a practical impossibility for now. But the warp drive isn't the only way to travel without moving by manipulating spacetime. Another big idea, also from the realm of general relativity, is the wormhole. Imagine you have a piece of paper. You draw two dots on it, far apart. If you want to get from one dot to the other, you have to trace a line across the paper. That's normal travel through space. But what if you could fold the paper so that the two dots touch? Then you could just step from one dot to the other without moving across the surface of the paper. You've created a shortcut. A wormhole is essentially a shortcut through space-time. It's like a tunnel that connects two very distant points in the universe, or even two different points in time, or even two different universes. Instead of traveling billions of light years across vast cosmic distances, you might be able to step into one end of a wormhole and emerge instantly, or almost instantly, at the other end. The idea of wormholes goes way back to Einstein himself. He and his colleague Nathan Rosen described something called an Einstein-Rosen bridge in 1935. These were theoretical bridges connecting different regions of space-time. The problem was these early wormholes weren't traversable. They would pinch off and collapse too quickly for anything, not even light, to pass through. Later, in the 1980s, physicists like Kip Thorne started thinking about traversable wormholes. These are wormholes that would stay open long enough for a spaceship or a person to pass through. And just like with the warp drive, the key to keeping them open and stable to preventing them from collapsing is exotic matter. You see a pattern here. To bend or shape space-time in these extreme ways, to do things like create warp bubbles or hold open wormhole throats, you almost always run into the need for this hypothetical substance with negative energy density. It's the magic ingredient that makes these impossible-sounding things possible in theory. Without exotic matter, a wormhole would snap shut faster than anything could cross it. It would be like trying to walk through a door that closes the instant you touch it. The exotic matter would act like a kind of scaffolding, propping open the throat of the wormhole against its natural tendency to collapse. What would it be like to travel through a wormhole? It's even harder to imagine than a warp drive. With a warp drive, you're always in normal space, just being carried along. With a wormhole, you're entering a tunnel where the very geometry of space is warped beyond recognition. Would it be smooth? Would it be turbulent? Would you see bizarre, distorted views of the universe as you pass through the throat? We simply don't know, but the appeal is clear, truly instantaneous travel. You step in, you step out. The distance becomes meaningless. This would change everything about our place in the universe. Suddenly, the entire galaxy, perhaps even beyond, could be within reach. Resource gathering, scientific exploration, even meeting other intelligent life forms could become a reality. However, the challenges with wormholes are just as immense, if not more so, than with warp drives. First, creating one. How do you even begin to punch a hole in space-time and connect it to another distant point? Where do you get the energy to do that? And how do you ensure the two ends connect to the right places? Imagine opening a wormhole and ending up inside a star, or in the empty void between galaxies. Then there's the stability issue. Even with exotic matter, keeping a wormhole open and traversable for a long time would be an incredible feat of engineering. What happens if the exotic matter dissipates, or the wormhole becomes unstable while a ship is inside? That would be a catastrophic end. And wormholes also bring with them even more profound time travel paradoxes. Because a wormhole connects 2 points in space-time. If you can move one end of the wormhole relative to the other, for example, by accelerating one end to near light speed and then bringing it back, you could theoretically create a time machine. This could allow for travel into the past, which brings with it all the mind-bending paradoxes we talked about. This is why many physicists suspect that either wormholes are impossible or there are fundamental laws of physics we don't yet understand that would prevent them from being used for time travel. The common thread in both warp drives and traversable wormholes is our understanding of gravity, as laid out by Einstein's general relativity. Before Einstein, gravity was thought of as a force, like magnetism, but Einstein showed us that gravity isn't a force at all. It's a consequence of mass and energy curving space-time. Think of a bowling ball placed on a stretched rubber sheet. The bowling ball mass energy creates a dip in the sheet's space-time curvature. If you roll a marble nearby, it won't go in a straight line, it will curve inward towards the bowling ball. That's what gravity is. The bowling ball tells the sheet how to curve, and the sheet tells the marble how to move. So, when we talk about manipulating space-time to travel without moving, we're really talking about actively controlling this curvature. We're talking about taking the fabric of reality and stretching it, compressing it, or tearing it to create shortcuts or propulsion. This is a level of control over the fundamental structure of the universe that is utterly mind-boggling. The biggest hurdle, as we've seen, is always exotic matter. It's not just negative energy. It's matter that violates what we call the energy conditions that normally apply to all known matter and energy. These conditions basically say that energy density should always be positive and that gravity should always be attractive. Exotic matter, with its negative energy, would allow for repulsive gravity or strange warping effects. Does it exist? That's the billion-dollar, or perhaps trillion-dollar question. We have some theoretical ideas, but no concrete evidence of a stable macroscopic amount of exotic matter that could be used for these purposes. It might be something that exists only in quantum realms on scales too tiny and fleeting to harness. Or it might be entirely impossible, and our current understanding of physics is missing some deeper principle that forbids it. And even if exotic matter does exist, and we could somehow create or find it, the sheer energy required to manipulate spacetime on a scale large enough for a starship is another colossal problem. Think about what warps spacetime in the universe: stars, black holes, entire galaxies. These are objects of immense mass and energy. We would need to somehow replicate that level of spacetime distortion with our technology. This isn't just about building a bigger rocket engine, it's about designing a machine that can reach into the very fabric of reality and bend it to our will. The engineering challenges are staggering. How do you build a device that can generate and control these extreme space-time distortions with precision? What materials would it be made of? How would it withstand the forces involved? What happens if there's a tiny miscalculation? The consequences could be universe-shattering, or at least ship-shattering. The precision needed would be unimaginable. You're not just moving a physical object, you're reshaping the very geometry of the space around it. Any error could lead to disaster. Imagine trying to steer a ship by bending the entire ocean rather than just pushing water with a propeller. Then there's the question of safety. If a warp bubble or a wormhole generator were to fail mid-journey, what would happen? Would the ship be instantly crushed? Would it be flung across the galaxy? Would it simply stop, leaving you stranded light years from home? The risks would be immense, and the potential for catastrophic failure would need to be absolutely minimized. What about the interaction with the environment? If you're moving a warp bubble, what happens when it encounters a stray asteroid, or the gravity field of a planet, or the intense radiation from a star? Would the bubble be destabilized? Could it have unintended consequences for the objects it passes near? These are all questions with no easy answers. It's important to remember that these concepts, the Alcubierre warp drive and traversable wormholes, are theoretical. They exist in equations, on paper, within the established framework of general relativity. They show us that if certain conditions could be met, then travel without moving might be possible. But the leap from theoretical possibility to practical reality is immense. Many scientific breakthroughs start as theoretical ideas. Sometimes what seems impossible at one point becomes commonplace later. Think of flight, or splitting the atom, or going to the moon. But in those cases, the fundamental physics was already well understood. With space-time manipulation, we're pushing the very edge of our understanding, and relying on ingredients like exotic matter that we haven't even proven exist in a usable form. It could be that there are deeper, more fundamental laws of physics that we haven't discovered yet. Or laws that might outright forbid the creation of exotic matter, or that impose other restrictions that make warp drives and wormholes impossible in practice, even if they're theoretically allowed by current models. In quantum gravity, a theory that aims to unify general relativity with quantum mechanics might hold the key. We don't have a complete theory of quantum gravity yet, and it's possible that when we do, it will tell us something definitive about these extreme space-time manipulations. So for now, the dream of travel without moving remains firmly in the realm of science fiction. It's a powerful dream, though. It taps into our deep-seated desire to explore, to overcome limits, to connect with the vastness of the cosmos. It makes us think about what's truly possible and what the universe might yet hold in store for us. The idea that we could bend and reshape the very fabric of space and time is a testament to human imagination and our relentless curiosity. It shows us how deeply we want to break free from the constraints of distance and the slowness of light. Even if we never build a warp drive or a stable wormhole, the pursuit of these ideas pushes the boundaries of our knowledge. It forces us to think about gravity, energy, and the fundamental nature of reality in new ways. It prompts new questions, new theories, and new experiments that might lead to unexpected discoveries, even if they're not directly related to interstellar travel. So, can we travel without moving? In theory, yes, according to our current understanding of physics. Concepts like warp drives and wormholes suggest ways to manipulate spacetime itself, shrinking distances or moving us along without us ever having to accelerate to incredible speeds. But the practical reality is a different story. It requires exotic matter we don't have, energy levels we can't fathom, and engineering capabilities far beyond anything we possess today. It's a beautiful dream, a profound challenge, and a powerful inspiration. It reminds us that even when faced with the seemingly insurmountable distances of the cosmos, the human mind will always find a way to imagine a path forward, even if that path involves bending reality itself. Maybe one day, our descendants will step into a bubble of warped space and feel the universe move around them, effortlessly carried across the stars. Or maybe it will always remain a dream, a theoretical possibility that sparks our imagination, but stays just out of reach. Either way, the journey of thinking about it is worthwhile. It helps us understand the universe and ourselves a little bit better.